Hello everyone, I'm Hong Hao. I will introduce our paper, Streaming Algorithms with Large Approximation Factors. It's a joint work with Yi, David Woodruff, and Yuheng Zhang. In this talk, I will first give an introduction to the background of our paper, then I will give an overview of our results. Finally, I will give an overview of part of our techniques. In the classical data string setting, we assume there's an underlying frequency vector x, which initialized to be 0. Then length string consists a lot of updates as the form iw, meaning that we plus a w to the ith coordinate of the vector x. We assume that during the whole string, the coordinate of the x is smaller than m. At the end of the string, we ask to a 1 plus epsilon approximation for the fx. Here f is a specific function. Here our goal is to use much less than the trivial n worth of the space, which is required to store the whole x. The classical data strings problems include the following: the distinct elements, where we want to know the number of the non-zero coordinate of x; the FP estimation, where we want to know the UG-LP norm of the x; and the L2 heavy hitter problems, where we want to identify a subset of 1 to n such that it contains most of the heavy hitters of the vector x. While a large body of the work has resolved the space complexity for many data string problems for epsilon between 0 and 1, for certain applications, the lower bounds of the space complexity may be too large to be useful. For such applications, it's therefore natural to allow for a large approximation factor alpha, which is larger than 1. Another motivation is the application to the linear augmented algorithms design. The linear augmented algorithms can be seen as a combination of the classical algorithms and the modern machine learning, where we aim to get the benefits from the machine learning advice. It has been shown that under the help of a heavy hitter oracle, which can indicate the subsets of the coordinates of the heavy hitter, we can reduce the space complexity of many data strings problems significantly. The heavy hitter oracles are learned by the machine learning methods and could be bad in the worst case. Hence, if we have a large approximation factor algorithms which runs in a much smaller space, we can run that in parallel, which will safeguard the linear augmented algorithms with a worst-case guarantee. Hence, here we ask our main questions. What is the space complexity of the classical streaming problems when approximation factor alpha are much less than 1? Now, we give an overview of our results. For the distinct elements problems, we show omega t space lower bounds for n to the 1 over t approximation. We also give the OT log m space upper bounds, which matches the lower bounds up to log m factor. For FP estimation, when p is smaller than 2, we show that the omega log n space lower bounds for poly n approximation still holds if m equals to poly n. We note that this is the same space amount of a constant approximation. Further, we also show that such lower bound also holds for the random order or the bounded deletion models. For the FP estimation when p is larger than 2, we show a tight space complexity of the n to the 1 minus 2 over p over alpha squared for alpha approximation. For L2 heavy hitter problems, in original problems, we consider the following condition. We want to identify a subset of n such that S contains every I for the 1 over k heavy hitters, and S do not contain any I such that Xi is not a 1 over 2k heavy hitters. It's known that the space complexity is k log n log m with error probability 1 over poly n. Here we consider alpha approximation L2 heavy hitter problems, which do the following reaction. The first condition is the same. H contains every I such that the Xi is a 1 over k heavy hitter, and S do not contain any I such that the Xi is not the 1 over alpha k heavy hitters. And we show that for any alpha is smaller than or tilde n over k, the k log n log m space lower bound continuous holds if the error probability is 1 over poly n. We also study some other problems like the estimation the cascading norms or the short NP norms of a matrix A, as well as the rectangle FP problems. For more details, please refer to our papers. Now, we give overview to our techniques for part of our results. We first consider problems of the FP estimation when P is smaller than 2. Our lower bounds based on a reduction from the coin problems introduced in the work of BGW20. The coin problems is as the following. Given a sequence of independent coin flips with either a high probability of 1 or 2 plus beta or 1 or 2 minus beta, we want to distinguish the two cases with high constant probability. This has been shown in the work of BGW20, such as it requires an omega log n beta of space when beta is close to 1 over square root n. And in the follow-up work of the BGC21, we know that it still requires omega log n beta of space when beta is smaller than n to the minus 1 over 3 minus epsilon. Now we construct our hard instance. Initially, the first coordinate of the x has been set to the 2n betas, and the remaining coordinates is set to 0. Then, given a sequence of the coin flips, we perform plus 1 or minus 1 to the first coordinate of x, which depends on whether the coin is a head or a tail. We can get, in this case, and finally, the x1 will become 4n beta plus minus all square root n in the first case, and in the second case, the x1 will finally become plus minus all square root n, which results in an alpha factor difference when 4n beta equals to omega alpha square root n. And recall that in the BGG21, we know that it requires omega log n beta of space to resolve the coin problems when the beta is smaller than n to the minus 1 over 3 minus epsilon, from which we can get the omega log n lower bounds when alpha is smaller than m to the 1 over 6 minus epsilon, which actually imply an omega log n lower bounds for a Polian approximation when the m is equals to Polian, which is the common setting in the data stream model. We know that the earlier lower bounds for the coin problems in the BGC20 only considers beta close to 1 over square root n, which only translates into alpha equals to theta 1 at best, which is not useful in our case. And the newer results of BGG21 shows omega log n bits lower bounds for beta smaller than n to the minus 1 over 3 minus epsilon, and such beta will translate into alpha equals to n to the omega 1, which is our desired. This is indeed the first application of the new result of BGG21 to the data streams problems. We turn to the FP estimation problems when P is larger than 2. We first consider the upper bound side. Suppose that we want an alpha approximation here, where the alpha is not too large. Otherwise, the problems becomes trivial. Then, let Q to be the numbers such that the n to the 1 minus 2 over Q equals to n to the 1 minus 2 over P over alpha squared. From this quantity, we have that Q is between 0 and P. From the inequality of the norm, we have that the Q's norm of x is larger than the P's norm of x. Next, from the definition of alpha and the Holder's equality, we have that the Q's norm of x is smaller than alpha times the P's norm of x. Combining these two things, we indeed get that the Q's norm of x is the alpha approximation of the P's norm of x. Hence, we can then turn to estimate the Q's norm of x. As mentioned, one motivation of the large approximation factor is the application to the linear augmented algorithms design. In the works of the JLL plus 19, it has been shown that we can have O tilde n to the 1 over 2 minus 1 over p algorithms for the LP estimation problems and have hit the oracle. The key observation here is that when the oracle is bad, the outputs tend to be an underestimation. Hence, let alpha equals to n to the 1 over 4 minus 1 over 2p. We can run an alpha approximation algorithm in parallel, and we finally take a maximum of the two outputs of the two different algorithms. We can show that we finally get a learning-based algorithms with the alpha worst-case guarantees. Now, we turn to the lower bounds. Actually, a reduction from the gap in infinity problems in BIK04 is enough to give the omega n to the 1 minus 2p over alpha square lower bounds. To get a tighter lower bounds, we consider the following version of the multi-party disjoint problems in WW15. There are S pairs, each has n bit binary streams, and for no instance, all coordinates are the Bernoulli random variables independently, and for a yes instance, we pick a random coordinates and set the such coordinates of all the binary vectors to be 1, and all other coordinates remain the same. And all the pairs will simultaneously send a message to the referee. Then the referee decides a yes or no yes test. It has been shown in the work of WW15. This problem requires omega n over s bits of total communications for a constant failure probability. We note that for no instance, after taking a union bound, we can show that with high probabilities, all the coordinate of the sum of the x is smaller than c log n over log n, while for a yes instance, the ith coordinate of the sum of the vector is equal to s. Hence, we can get a separation if the value of s is large, and we will set the value of s according to the value of alpha. To get the extra log m factor in the lower bounds, we consider the following augmented version of the disjointness problems. The players receive r instance of the xi, and the referee will receive an xt, which is not known to the players, but in addition, last are minus t of the impulse vectors of the players. At the end of the protocol, the referee needs to determine the tth instance is a yes instance or a non-instance. And in the work of WW15, it's been shown that it requires roughly omega rn log 1 data over s bits of the total communications when the delta is not too small. To reduce to the streaming, the authors of the WW15 use the results in the LNW14. Roughly speaking, the LW14 shows that under some reasonable assumptions, the algorithm to the streaming problem can be converted to a path-independent algorithm. Here, the path-independent means that the output of the algorithm only depends on the initial and the final settles of the underlying vector. Or in other words, the order of the updates will not change the difference of the output of the algorithms. And after having the path-independent properties, the referee can infer one possible vector settles for each player and do the corresponding updates. Now, a brief discussion on reduction. Suppose there is a streaming algorithm A which gives the alpha approximation to a piece norm of the x. Each player will perform updates based on their vectors. Then they will send the memory contents to the referee. We note that in the augmented settings there are total t instances for each player, and for each player j and for the ith instance, the player j will multiply the 10 to the I minus 1 when performance updates to A. Or in other words, the underlying vector of the jth player looks like the following. The intuition of this expression is that it will make the first t minus 1 instance are not enough to affect the results of the tth instance, and the referee know the input of the last I minus t instance in augmented setting. Hence, he can do the corresponding updates to cancel the effects of them. And we show that by setting x equals to alpha to 1 over p times n to 1 over p, and R equals to log MOS. There's an alpha separation between the piece power of the piece node of the Y. Here's Y of the sum of all the vectors from all the places, which will yield a targeted response. For more of our results, please see our papers for more details. Thanks for the listening.